We'll start with today's session on math with words. This is a session in this is a lesson in natural language processing, and what we are going to see is how we are going to be able to play around with words. And the first thing that we need to understand is that every NLP application or machine learning application consists of a pipeline. What you're seeing on my screen is a chatbot recirculating recurrent pipeline. Now, first, when the text comes, what do you do with it? You parse it. You get the tokens from it. You use regular expressions to understand if it has any familiarity with what expressions you have in mind. You tag it. You tag it in terms of you tag it with labels such as nouns, pronouns, adjectives, verbs. Named entity recognition. You get the named entities such as organizations, geopolitical entities, any human names, any common nouns, any names. From it, you extract information and reduce dimension. Now, as part of this parsing, all of this parsing goes into a second step. That is analyze, check spelling, check grammar, analyze sentiment, analyze humanness, analyze style, and then you produce a scored statement. Now, before we produce a scored statement or we analyze, we have been on this first step mostly. What are we going to do with once we have produced tokens? We have got vectors from it, kind of by getting the one second. Yeah, am I audible?
Yes, please.
Okay. Okay, so we were at parse thing. Now, when you parse a statement, we would see all of this happening in our following slides. That we would get some text, we would parse it, we would produce tokens, and we would try to understand what it means. Now, before we do that, we need to be familiar with certain terms, and the first term is bag of words. What is bag of words? Bag of words is that when you get a statement like hi, like this statement over here, the faster Harry got to the store, I'd put it in bold. The faster Harry got to the store, the faster would get home. This is a sentence that we have, and uh, we would tokenize it. Basically, by tokenizing, we are using the NLTK package, and when we are using NLTK package, we produce tokens. The tokens are essentially words and punctuations present in this sentence. So there is nothing fancy about bag of words. It's just that you count them after getting the words from the input text. You count them, and over here you can see that the word the is appearing 4 times, faster is appearing 3 times, Harry is appearing 2 times, got to store, comma, would get home, dot is appearing, all are appearing 1 time. This is essentially what you get from a bag of words model. Whenever you hear the word bag of words, hear the terms bag of words, it's also sometimes abbreviated as bow. And next thing that comes is term frequency. Term frequency is that once you have the word, what do you do with it? Well, the term frequency is basically the number of times, the number of the number of times the number of times the word appears in the text divided by the number of words in the text. The number of words in the text. Now, there is nothing fancy about it, but it's still very useful. Delete 1 second. So this is term frequency, and we'd calculate it from our bag of words model. When we have our bag of words model, what we were getting keys and values. As we see over here, we have a dictionary, and this dictionary has some keys and associated number of number of times those words occurred in the text. Now, when we have to calculate the term frequency for them, we have to get those values and get those keys, and we have to know the length of our text. Now, when we know the length of our text, what we would simply do, we divide the keys, every element in keys k by L, and this is the piece of code that is doing it. And essentially what we're computing for every word is that we just divided 4 by the length of the text k, and this is the formula given over here. And term frequency is a decimal number that essentially is a fraction, and this is the Python code for doing that. This is the formula: the number of times a word appears in the text divided by number of words in the text. Next thing that comes is cosine similarity. Cosine similarity is that in Python it would be a dot b, and this is a bit of a, we remember this formula in mind, that cos theta is equals to a dot b divided by mod of a multiplied by mod of b. Now, if you want to do a dot product, you take mod a and mod b onto the other side of the equation, and you get a formula. So that looks like this. I put it in bold, and we have used NumPy package to get the norm of A, linear algebra package, norm of A, norm of B multiplied by cos theta, cos of theta. Theta is the angle that is produced, that is cos theta is the angle between A and B. Now you can do it in pure Python as well. This is for your reference. I'd put it on blog as well. You don't we don't have to necessarily discuss it over here, but just to give you a brief of it, what it does is, you have got the values of, once you have the vectors, which are essentially numbers, what you do, you enumerate all of them, and you are producing a dot product for them. Now, how do we get the dot product? This is bit of doing plain mathematics for it, but basically this is you can do it using package as well. Otherwise, we can do it with plain algebra also, plain BODMAS also. Now, Zipf's law is that frequency of a word, frequency of any word is inversely proportional to its rank in the frequency table. What does it mean? Now, what it means is that if you have a word, let's say B, which appears on the rank 1, and let's say you have a word called of, and you have a word, let's say Harry, and then appears on the third number of times in your text. Now, if you have a large corpus, what you would see is something like something happen like this. That if is if you have, let's say, words on each of words to represent the ranks of words to represent all of the words, this okay the way the drop will come in the, and then we would have to come here, so we connect it like this. Okay, one third. So basically it is inversely proportional. If we take the curve for producing the frequency distribution versus the rank would be somewhat like this. If you instead take the logarithms, it would be a curve like this. Sorry, like this, a straight line like this. The way, if we have to put it in numbers, then I'd put it in numbers also. Frequency f of a word equals to inversely proportional to the rank k, constant k, divided by rank r, where k is a constant and r is the rank of the word. Now we move on to the next slide. IDF, inverse document frequency, and term frequency, TF-IDF, term frequency hyphen inverse document frequency. Now, what will happen? This slide is presenting you with the formula for what we learned, the term frequency that we learned. That term frequency for a text T is token T, for document D is count of the number of times the token T appears in the document divided by the number of the number of words in the document D. IDF is inverse document frequency, is that if you have a large corpus with multiple documents, then the number of documents in which the term T appears, logarithm of number of times, number of documents in which the term T appears, divided by the number of documents containing the term T. And TF-IDF is simply the multiplication of TF and the IDF scores for term T, document D, and corpus capital D. A summary of what we have learned over here is that any web scale search engine with millisecond response has the power of TF-IDF document matrix hidden under the hood. Term frequency must be weighted by their inverse document frequency to ensure the most important and most meaningful words are given the heft they deserve. Zipf's law can help you predict frequency of all sorts of things, including words, characters, and people. The rows of TF-IDF term document matrix can be used as a vector representation of the meanings of those individual words to create a vector space model of word semantics. Euclidean distance and similarity between pairs of high-dimensional vectors. Cosine similarity is an important one. Cosine distance, the amount of overlap between two vectors, can be calculated efficiently by just multiplying the elements of normalized vectors together and summing up those products. Then practical one, we have a practical also in which we use, this is a paragraph about kite, and we have assigned it to a variable txt1. Then we have another paragraph about kite, and we assign it to variable txt2, and the language we are using is Python, and then we use the scikit-learn package to get the TF-IDF vector for it. This is our corpus containing txt1 and txt2. This is our vector. This is our initial variable holding TF-IDF vectorizer. Over here we have fit. We call the fit transform method on the vectorizer, and we get a sparse matrix of numpy float integers, which basically is the numbers representing the TF-IDF scores of the corpus we have with us. Now we have called some methods on. We are able to get the feature names and get the number of features we have, and then we move on to calculating the cosine similarity between the two texts. We have a text1 and text2. We transform our individual text using the vectorizer we trained earlier and try to get the cosine similarity between them. Cosine similarity is again a functionality given by sklearn scikit-learn package, which you can see over here. Earlier we had used TF-IDF vectorizer, and in this statement, we are using cosine similarity. Now, finding meaning in word counts, that is the semantic analysis. That is what that is what we do in semantic analysis. And the way to do is that the first we have to identify why do we need to do the semantic analysis. So this slide talks about that, the problem with TF-IDF, words that mean the same. TF-IDF vectors count the exact spellings of terms in a document. So texts that restate the same meaning will have completely different TF-IDF will have completely different TF-IDF vector representations if they spell things differently or use different words. This messes up search engines and document similarity comparisons that rely on count of tokens. Now, polysemy, this is an important problem, not a problem, but a feature of English language, that English is a fuzzy language. We have one word and many meanings. This is what polysemy is. The existence of words and phrases with more than one meaning. English is a fuzzy language, and many languages are fuzzy, not just English. Then there are more problems like polysemy. Some of them are like homonyms, words with same spelling and pronunciation but different meanings. Zeugma, use of two meanings of a word simultaneously in the same sentence. Homographs, words spelled the same but with different pronunciations and meanings. Homophones, words with same pronunciation but different spellings and meanings. So imagine if you had to deal with a statement like the following: she felt less, she felt stamped down, dim, more faint, 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 pain. And this statement was given by Patrick Ross. Now, next we cover an algorithm to, it is just, we are beginning to solve the problem in the next sessions. In the coming sessions, we talk more about on how we can deal with problems. But in this next coming slide, we'll talk about linear discriminant analysis. Now, linear discriminant analysis breaks down a document into only one topic. How does it do that? If you have, because it's one dimensional, LDA doesn't require doesn't require, you can just compute the, so basically you compute the average of each side of binary class. You haven't been, so the thing about LDA is that it's one dimensional. You just compute the centroid average mean of all your TF-IDF vectors for each side of a binary class like spam and non-spam. Your dimension then becomes the line between those two centroids. The further a TF-IDF vector is along that line, the dot product of the TF-IDF vector with that line tells you how close you are to one class or another. LDA classifier is a supervised algorithm, so you do need labels for your document classes, but LDA requires far fewer samples than fancier algorithms. For this example, we show you a simplified implementation of LDA that you can find in scikit-learn. The model training only has 3 steps. So you will just do them all directly in Python. There's only 3 steps. Compute the average position centered of all the TF-IDF vectors within the class, such as spam, SMS messages. Compute the average position centered of all the TF-IDF vectors not in the class, such as non-spam SMS messages. Compute the vector difference between the centroids, the line that connects them. All you need to do to train an LDA model is to find the vector line between the two centroids for a binary class. LDA is a supervised algorithm, so you need labels for your messages. To do the inference or prediction with that model, you just need to find out if a new TF-IDF vector is closer to the in-class spam centroid than it is to the out of the class non-spam out of the class centroid. That was all we had for today. Thank you for joining. See you in the next session.